The first light to ever flow freely through the universe is the cooled residue known as the cosmic microwave background, or CMB. The Big Bang was followed by the release of this fossil radiation, which is the farthest that any telescope can observe. It is regarded by scientists as an afterglow or shockwave of the Big Bang. Welcome back to my channel. The cosmic microwave background radiation is far from revealing all its secrets. Although far-fetched, there are some valid assumptions that leads to the idea of having something artificial in nature, or presenting some signs of other universes. In 1965, the CMB radiation was unintentionally found. American radio astronomers Penzias and Wilson detected a signal in their radio telescope that was impossible to assign to a specific source in the sky. Day or night, summer or winter, it seemed to have the same intensity everywhere. In their opinion, the signal had to originate from somewhere outside of our galaxy. Turned out that it originated at the beginning of the universe. They viewed their discovery as strong support for the Big Bang idea. According to this hypothesis, the shockwave of that primordial explosion is still audible today. As of now, only the Big Bang theory can satisfactorily account for the CMB's existence. This theory holds that the universe began as a very hot, dense phase that gradually expanded and cooled. For many 100,000 years, the temperature was too high for atoms to form. The cosmic microwave background is nearly equally bright in all directions. The COBE satellite, which measured an almost uniform temperature of 2.7 Kelvin over the sky, corroborated this. However, the very fact that other galaxies exist suggests that there should only be very slight variations in the CMB's measured temperature. The seeds for the development of the galaxies that we see today would have been provided by these modifications or fluctuations. Up to 5 millionths of a degree in size, these minute variations will be detectable by Planck. But it turns out that finding the CMB was not as challenging as it might seem. Once it's discovered, can be studied, and it turns out that you can see the CMB on your own, albeit dimly, using your own TV. All you need is an old, analog monitor that requires an antenna, and about 10% of the static, if you have it tuned to static, is brought on by the CMB. Since the CMB's discovery, research into it has uncovered a number of mysteries that could provide answers to some extremely important issues about the universe. Why the CMB looks uniform. It's crucial to remember that beautiful and flawless at first, it contains minor and subtle variations that, by themselves, are very significant and fascinating. The variations in temperature, the cold and hot spots, it appears to have occurred in a manner that allowed for the uniformity we observe today by keeping in touch during the early stages of the universe's expansion in regions of the universe that are now very far apart. As a result, the concept of cosmic inflation has been developed to account for this apparent era of extremely rapid expansion of the universe. This raises a completely new set of inquiries. But what brought about inflation? How come it stopped? While many predictions of inflation have been confirmed, this may be a mystery that can be resolved by further research on gravitational waves and better resolution CMB mapping. The new era of CBM observations starts with the Planck satellite, the anisotropies of the cosmic microwave background, or in short the CMB as observed by Planck's satellite, is a snapshot of the oldest light in our universe, imprinted on the sky when the universe was just 380,000 years old. It shows tiny temperature fluctuations that correspond to regions of slightly different densities, representing the seeds of all future structure, the stars and galaxies of today. Its uniformity is a relative. The CMB has incredibly minute variations that contribute to even bigger mysteries for which we may never have the solution. The cosmic background radiation of the universe had enough energy just 15 million years after the Big Bang to keep the entire universe at a comfortable 300 Kelvin for 3 million years, which was sufficient to support liquid water everywhere. There was a possibility that life may exist everywhere in the cosmos during this cosmologically tiny period of time, without necessarily needing to orbit a star for energy. This would have been very distinct from our current standard of living in terms of habitability. However, it is at least conceivable that microscopic life may have briefly established itself. The response is possibly, but very simple microbes are extremely unlikely to exist in the conditions of the early universe. However, in that era, the time could have flown differently, being in the near vicinity of a singularity, the Big Bang, and who can tell if an intelligent entity or civilization could have had or not enough time to arise and evolve. Everything in the universe was close relative to each other. Could that civilization would have been able to leave a mark by moving matter in a way that, for a later civilization to detect these signs in the CMB? Sadly, if there was ever any proof of this existence, it is most likely long gone. And we'll always ponder what might have been in the past. The cold spots in the CMB are truly staggering. The difference in temperature poses some issues, like the size of the temperature variations, which may only be caused by chance fluctuations, but seem remarkably large for a random event. Some scientists ask, what if the cold spots are not random? Should be the imprint of another universe pushing into, or colliding with our own? The standard cosmological model does not readily accommodate non-random cold spots of this size and nature, so if they are not random but rather represent a physical process that produced them, that no longer quite fits, and would instead suggest new physics if we are to refute the artificial nature of them. The problem is that there isn't a viable model to explain it in terms of physics, and neither one has emerged so far. The other riddle involving cold spots in the CMB is a particularly strange one, also known as the CMB cold spot. This specific cold spot differs from the majority of the other cold regions of the CMB in that it is both oddly large and encircled by a relatively hot ring. There are two primary explanations for this. One is that observations of the CMB in this region are being impacted by a massive supervoid, one of the largest structures in the cosmos, if it exists. Some studies, however, have questioned this, and the void may not exist, may be illusory due to some observational issues, or may in fact be a remnant of something primordial that occurred in the early history of the universe. But there is an additional choice. It's also conceivable that it could be an imprint of a different universe. The concept is that our universe was initially linked with another universe through quantum entanglement, and after the cosmic expansion, they were split apart. The inflation theory looks a lot like a decoherence, a fast scrambling, the growth of the complexity just driven the expansion faster than the speed of light. There's one option that may help to solve some of the mysteries we already know about, while also creating some new ones. All of this is connected to Professor Roger Penrose, whose conformal cyclic cosmology, an alternative cosmological paradigm within general relativity. The idea is that instead of a single Big Bang and resulting universe, there are iterations where there is a cycle of Big Bangs and resulting universes one after another for infinity. If this is an accurate description of what actually occurs, which is disputed, though there is some claimed evidence for it, then a Big Bang occurs, a universe exists and eventually decays, and then another Big Bang occurs. Several marks, including our own, ought to be left on the CMB after each iteration. The Fermi paradox, which appears to be a contradiction between the lack of evidence and the high probability estimates for the presence of extraterrestrial civilizations, was also examined by Gerzadian and Penrose in 2015. The cosmic microwave background in conformal cyclic cosmology offers the potential for information flow from one aeon to another, including sentient signals according to the idea of information panspermia. Anomalies in the CMB could be explained by Hawking points, remnant signals from the Hawking evaporation of supermassive black holes in a universe prior to our own. Several marks, including our own, ought to be left on the CMB after each iteration. Thank you for watching. Join me next episode to unveil other interesting facts of our universe.